Welcome to the first open lecture from the Simons Institute for the Theory of Computing for this semester. Today's speaker is Peter Bürgisser from the Technical University of Berlin, who's one of the organizers of the exciting program that's being run this semester on algebraic geometry and its relations to computer science. And to introduce Peter in more detail, the local organizer of the program, Ben Sturmfels, is going to take it.
Yeah, I'll keep it brief. So it's called Algorithms and Complexity in Algebraic Geometry. And Peter is our lead organizer, so he has done a lion's share of the work, and it's been really wonderful so far. There will be four public lectures altogether, 2 from the concurrent program in spectrograph theory, and 2 from our program. The second one, perhaps a bit more on algorithms, by Ottaviani, and the first one by Peter. So Peter received his PhD in 1990 in Konstanz under the supervision of Volker Strassen, and he is a world expert in algebraic complexity theory. He's written 2 books on algebraic complexity theory. His postdoctoral trail also took him through Berkeley, through ICSI, and in recent years he has been a professor in Paderborn for many years, and now since 1 year in Berlin. He's had numerous honors, including was a speaker at the ICM in Hyderabad. He has had many successful students, some of whom we enjoy having here in Berkeley. And without further ado, geometry, invariants, and the elusive search for complexity lower bounds.
Thank you very much, Bernd, for these kind words. And it's great to be back in Berkeley. The Simons Institute is a wonderful place, and I'm sure we'll have great discussions there, and we'll forward our field. So it's my task to give an overview over this program. And it's not an easy task because the topics are quite broad. And as Bernd already mentioned, there will be another open lecture. So in my lecture, I will focus on the complexity aspect, more specifically on this difficult task of how to prove complexity lower bounds. And there will be another talk on other aspects, which possibly also will be more applied. So let me start with the motivation. Okay. I will talk about evaluation of polynomials. So I have these 3 examples of multilinear polynomials. So variables x1, x2, up to xn here. And let's have a look at this. This is called an elementary symmetric polynomial. So out of these n variables, you pick k variables in all possible ways, take the product and sum. So you have here a summation, which if k is, say, n½ you have exponentially many summons. Okay? The second polynomial is familiar to everybody in this room. It's a determinant. You sum over all permutations of n symbols, take this product of the variables, and then you decorate it with this sign, which is very important. This is a determinant. And if you forget the determinant, make it simpler, put a 1 here all the time, you get another polynomial, which is maybe not so familiar to all of you in the audience. This is called the permanent. Okay? So the task is, we want to compute these polynomials arithmetically. So we have additions, subtractions, multiplications, maybe also divisions if we want. And the task is to compute these polynomials with as few arithmetic operations as possible. Okay? So let's have a look at the example. What can we do here? Let's first take the first one. One has to be a little bit clever. So there is the following well-known idea. You take another variable, call it t, and you form this product of these linear factors, t plus x1 times t plus x2 and so forth, up to t plus xn. And then if you expand this sum and you think for a moment, then you realize that the coefficients of this polynomial, seen as a polynomial in t, are just these elementary symmetric polynomials. Okay? Now, this polynomial, of course, is very easy to compute. It's just a product of n factors. So you compute it with this many operations. I guess all of you know the O operation just means bounded by a constant times n. Okay? Now, if you you choose n+1 values t here, and you evaluate these polynomials at these values, okay? And once you have those, you retrieve the coefficients of the polynomial by interpolation. So basically, you solve a linear system of equations, and then it's very easy to see that you can do with that many operations. N cubed, say, for the linear algebra, and n squared for this evaluation. So this is polynomial time, okay? Bounded by a polynomial in n, okay? The determinant. Very important fact that the determinant can be computed with a polynomial number of arithmetic operations. So if we use Gaussian eliminations, which is everybody learns in the first year study, then n cubed operations. Okay, we all know that. There are some divisions involved here, but that's not so important here. Okay, so that's a very important fact that this is that this you can compute so efficiently because all of the linear algebra is basically relies on that efficient computation. Okay, how about the permanent? The permanent is more tricky. If you remember the definition, it was a sum over all permutations, so meaning you have n factorial terms. So if you do it in the stupid way, it will be something like n factorial. One can do some tricks and bring it down to 2 to the n. This is a trick due to Reiser. Use some inclusion-exclusion form in a clever way. Then you get this, the 2 to the n, but we don't know how to get it further. Okay? So this is state of the art. We don't know how it's better. Why it's important to compute the permanent, we'll tell you later. Okay. How about optimality? Yeah, the question is, can we do even better? For this, we have this notion of complexity. I denote it by LF. L stands for length. This is the minimal number of arithmetic operations that are sufficient to compute the polynomial f, starting from the variables and field elements. The field elements are thought of as being constants. Okay, this is the definition of complexity. Right. So now, back to the elementary symmetric polynomial, one can be a little bit more clever. Yeah, one can do, probably many of you know that one can choose this ti as roots of unity, and there is the fast Fourier transform, very important algorithm. And if you use that, you can bring it down the complexity to essentially linear up to a logarithmic factor, okay, n times log square n. Okay? So this is very important for application. And what is nice here and remarkable for this problem, we have a lower bound which is almost matching. Okay? This is essentially optimal. So we know a lower bound of the order n log n. You have this capital omega. It just means greater than or equal a constant times n log n. And this is due to Volker-Strassen and Bauer-Strassen. And the argument is based on algebraic geometry, more specifically on the degree of varieties. And I think this is probably, this paper by Strassen was the first time that algebraic geometry was used with the goal of proving a complexity lower bound. Okay, so good. Right, but I don't want to go into details of this here. Yes?
Actually, the bound is precise for multiplication.
I was thinking about, when should I say it? You're right. If we count the multiplications, then the upper bound is n log n, the lower bound is n log n. It's just a question of the constant factor. So it's optimal. Okay, thank you. Good. Let's move on to the determinant. So in a sense, this problem we understand up to this log factor. The determinant is more difficult. A very basic function, but most of you probably will know that, again, Strassen, he wrote an influential and seminal paper in '69 with the title Gaussian Elimination is Not Optimal. And he discovered that you can replace the exponent 3 by 2.81. Yeah, by some kind of crazy algorithm, he came up with this, and people were puzzled by this. Okay, so actually, one can prove that the determinant has the same asymptotic complexity as the multiplication of matrices. So actually, we are talking here about the complexity of matrix multiplication. So that's a very famous problem, and there has been progress in it. A lot of progress in the 80s. And here I summarize what we have achieved so far. It is known that the complexity of the determinant is O of n to the omega. Omega is called exponent of matrix multiplication. And we know now that it is less than 2.373. It must be at least 2. So this is, okay, essentially going back to Coppersmith and Winograd in '87, but very recently there has been a slight improvement in this bound by Virginia Wasilewska-Williams. Okay, so it's a fundamental problem to determine this exponent, and the experts on this are involved in assignments. Probably are either here or they will show up for the workshops. And the conjecture is that this omega can be chosen arbitrarily close to 2. We don't know, but I mean, we believe there cannot be marvelous lower bounds because it's just like that.
Who does the choosing?
Probably God. Has been chosen already, but we don't know. Okay. Okay. The permanent. So why is it important, this permanent? Yeah? It doesn't have so nice properties as the determinant. The relevance comes from a universality property I'm going to explain very soon, but not now. So we don't know of any computation of this n by n permanent that takes a number of arithmetic operations that is sub-exponential in n. Unknown. Yeah? And Les Valiant, he came up with a conjecture in '79. He conjectured that the complexity of the permanent actually grows super polynomial in n. So that's, I think, one of the biggest conjectures in algebraic complexity theory. What can we do today? I mean, if you take the book on complexity by Arora and Barak, they have a chapter and they say proving lower bounds is Waterloo of kind of theoretical computer science. I mean, we are extremely good in designing algorithms, but lower bounds, it's the Waterloo. So what can we prove? So far, we cannot even prove a superlinear lower bound on this. Yeah? And I sincerely hope that as a result of this program, we will be able to improve the state of the art. Not resolving Valiant's conjecture seems too hard, but getting better, proving a nonlinear lower bound. I hope this should be possible. Okay. Now, let me tell you about some of the ideas. How can we prove lower bounds? Yeah? Let's trace back the ideas. So, also to the 70s. So what can we do? Let's have a look at this polynomial here. Again, sum over all permutations. We have this product. But instead of the coefficients here, ai, I pick them somehow. Okay, you see if this coefficient a pi is always 1, it will be the permanent. If it is changing the sign, then it's the determinant. But let's put here something generic if you want. Pick it at random. Yeah? Then it's not too hard to prove that, well, then that the polynomial will be difficult. So in a precise sense, one can prove that for almost all choices of coefficient systems, this polynomial has a complexity that is at least the number of coefficients. So this is a counting argument. Actually, the idea goes back to Claude Shannon, who he was the first to do such kind of argument in the context of Boolean functions. Okay, it's a counting argument, and we can do the same here. Okay, but the question is, how can this bound be extended to specific choices of the coefficients? Yeah? And here again, the result, again, Strassen, he did for the first time such a thing. He said, let's do the following. Well, it's not that he didn't state it exactly this way, but it's the techniques that he introduced. So let's take 1, 2, 3, 4, 5, etc. up to n factorial. These are integers that they take the square roots. And these are the coefficients of my polynomial. We put them in any order. Then one can prove that this polynomial is hard. Its complexity is bounded by a constant times n factorial over log n factorial. Okay. How do we do this? What is the proof? Let me give you an overview of the idea. Okay. It's important to explain in order to explain what's going on in this program. So what do? We are dealing with polynomials f of degree at most n in n square variables. Now, this polynomial is given by a list of coefficients. We think of it as a coefficient vector. It's a point in this space, c to the n. Okay, and n is this quantity. So the polynomial is a point. Okay. Now, important observation. We want to describe a set of polynomials with complexity less than r. Yeah? Easy polynomials. I can describe then, or this set of polynomials, I can describe as the image of an explicit computation map, which is a polynomial map. Yeah, it goes from c to the q to c to the n. Q is the number of parameters, and the number of parameters is quite small. It's basically r squared. So, okay. So I hope it's not too technical, but I try to, okay, I know many formulas, but let me explain what it is. It's quite simple. So, of course, there are many ways to do such a computation, but you can kind of normalize it. You can say, we start with the variables and constants, then let's do linear combinations. In the first phase, once I produce two linear combinations, then I take a product. Okay? Then again, I take linear combinations of what I have done, I take a product, and so forth. So this gives a normalization, and I have written it here. You see, I have a sequence of intermediate results. These are the g's. I take linear combinations here and here with coefficients a and b, and take a product. Okay? So these ai and bj are just the parameters, and if I count these parameters, I get this. Yeah? So that's the idea. It's a polynomial map, and it's easy to write down. It's completely explicit. But it's quite complicated. Yeah? So what is now the connection to algebraic geometry? So the set of polynomials that are easy, it's maybe not so easy to understand. So what we do, if you are a geometer, you say, let's take the closure of this set. So you add all limit points. That's completely natural for a geometer, and you get what is called an affine algebraic variety. So we take the so-called Zariski closure. And what is an affine algebraic variety? It's the solution set of a system of polynomials. This is important to remember. These are just solution sets of systems of polynomials. Okay? So we do this, we add these limit points, and then we get this variety, which I call XNR. So this is the set of easy polynomials plus the limits. Okay? Now, what is the basic strategy to prove complexity lower bounds? Actually, it's easy to understand. So we look for some function r from the space c to the n, which is the space of my polynomials, with complex values, that vanishes on the set of easy polynomials here. It vanishes here. Once I have, let me call, just to have a catchy name, let me call all these non-zero polynomial functions resultants. Okay? If I have a resultant r, I can do the following. Okay. If I want to investigate whether f is easy or not, I can try to evaluate the resultant at f. And if, for good luck, the result is non-zero, then I am sure that f is not in X and R. So I have proved a lower bound. And these resultants must exist just because the X and R is an affine algebraic variety. It's a zero set of polynomials. The question is how to find them. So this is very general, yeah? But that's the idea. That's the idea. So what can one do in our situation? Here again, the strategy. Okay, the point is, even though this computation map is quite complicated, we can control it. I mean, we see, they have these polynomials have degree that is growing most linearly in R. We know the bit size and so on. And as a result, well, if one does the analysis, one can deduce the existence of a resultant with a degree bounded by this and that. Okay? That's the proof that Strassen originally did. You prove there is a resultant, it has degree at most that. You don't need to know more about it. And if you have this existence, then you say, okay, if I plug in this strange coefficient vector consisting of the square roots, then R of f cannot be zero by some algebra, by some degree arguments. You deal with algebraic numbers. So you have to do some algebra to prove it. But that's the idea. Okay? But it's important to understand the basic idea of the resultant, and we only use the existence in a certain degree, nothing more. Okay?
For what value of R?
R?
For what value of R can you prove this?
For, the point is, I say there is a function, a resultant R. It's a polynomial function.
For which value of the little r?
The little r, n factorial over log n factorial. Excuse me, I understand. Okay, sorry. This is good. Right. Okay. So, okay, the question is, how can one possibly extend this? So in this example, the coefficients of f were algebraic numbers. Okay? A bit strange, yeah? A bit artificial. Can one possibly do more general? I mean, we want to have polynomials where the coefficients are integers. Okay? So one can come up with this definition of a p-definable family. Now we're looking at families. In complexity, you always look at asymptotics. So you have a family, f sub n, of multivariate polynomials. Think of the small n as the number of variables. And we say that the family is p-definable if the coefficient function can be computed in polynomial time. So somebody gives me the exponent vector, and then I can quickly compute what is the coefficient. For instance, for the determinant, somebody gives me the permutation, I just compute the sign, and that's easy to do. So this is this notion of p-definable family. And there is a result by Leslie Valiant, which is a consequence of a completeness result of the permanent. This result says, okay, replace this permanent by any family of p-definable polynomials. Yeah? If we manage for this family to prove a superpolynomial bound on the complexity, then we have proven a superpolynomial bound for the permanent. So the permanent captures the complexity of all these families. Okay? Good. So this somehow explains why the permanent is important. So let me, before I move on to a different topic, let me give you a curious example that somehow shows that the problem is rather delicate. Yeah? So here, look at this example. Here I have just one variable, x. So I take the polynomial with one variable with zeros, 1, 2, 3, 4, up to n. Okay, and then, okay, I replace x by x squared. So I have this polynomial here, product of x squared minus j. And then using high school algebra, I factor this as x minus square root of j times x plus square root of j. And I regroup the factors. So I can, as a result, this p and x, this integer polynomial, is factored as a product of two polynomials, fn and fn tilde. Okay? Now, using the same techniques as I told you right before, one can prove that both factors here are difficult. Now, difficult in this context means complexity at least n over log n. This I call difficult. Okay. Then it's very natural to, okay, conjecture or say, well, both factors are easy. So difficult, both factors are difficult. Let's multiply them. They will be difficult. Well, but can we prove it? And I remember when I was a postdoc in Berkeley, some 25 years ago, I was trying to prove this, I mean, just to extend this technique of Strassen, and I failed. But I didn't understand why. I mean, then later on, I understood why I failed, because then much later on, I realized the following connection. Okay, suppose we manage to prove a lower bound of the form n to the epsilon for this polynomial, for any positive epsilon. Then it would imply superpolynomial lower bounds on the complexity of the permanent. So I couldn't solve it, but somehow I knew why. This happens in complexity.
What's the best rule method to compute it?
It's related to factoring integers. It's related, so it's so what you can do with the square root of n and some logarithmic factors.
So the conclusion is so you can't prove that the x squared polynomial is hard.
The conclusion is somehow.
Even with each factor you can show, sorry, you can't.
Yes, it's somehow the conclusion is that you cannot extend this technique going to the multiples. If you go to multiples of polynomials, yes, something could happen. That's subtle somehow. maybe not so expected. Okay, permanent versus determinant. This is the flagship problem in algebraic complexity. It's a very difficult problem. Let me go through that briefly. So we have complexity classes, which were defined by Valiant. Nowadays they're called VP and VNP. And the objects are sequences of multivariate polynomials over some fixed field. Think of the complex numbers, fixed ideas. So we have a class VP. I don't want to define it formally. I only have an hour. But think of them as they capture problems of linear algebra, like the determinant family is contained in this class. So VP somehow describes the easy problems, and the class VNP describes problems from graph theory, combinatorics, statistical physics, quantum mechanics. These are all related to some enumeration problems, and the permanent is a member of this class. And then we have the notion of reduction. As in computer science, I mean, computer scientists are extremely good in making reductions, so we can compare problems. So we have a notion of reduction, and that allows us to talk about complete or universal objects. So this, a problem or a sequence is complete in a class if it's in the class, and all sequences in that class reduce to that one. Okay? And what Valiant proved, he proved that the determinant family is complete for VP and the permanent is complete for VNP. Okay? Okay. The experts in the audience may know that with the VP there is maybe a little problem here, that there are variants of it, but I don't want to enter it. Okay. So we have this beautiful result, and we have this hypothesis stating that these classes are different, and it can be seen as an arithmetic version of the famous PNP problem. Yeah? And this hypothesis, by these completeness statements, is equivalent to saying that the complexity of the permanent grows superpolynomial in N. So it's exactly that conjecture that I stated at the beginning of my talk. Yeah? And how is that related to the usual PNP? Well, it's not hard to prove that P different from MP implies, this separation, P different MP, implies VP different VNP over the complex numbers. And this means that, I mean, if you really want to prove P different MP, we better prove this first. So, yeah, we have this implication. And, okay, the idea is that it's an old idea that, I mean, if you are in this setting of the polynomials, you are close to algebraic geometry. Algebraic geometry, it's an enormous field. It's very old. There are many, many techniques, and hopefully one can use some of these techniques or develop them further to approach this problem. That's the hope. Yeah, that's the hope. Yes?
Over C quantifies VP not equal to PNP or the whole sentence?
Excuse me?
Over C. That quantifies the whole
Here.
sentence?
Here is yeah. Okay. Good. Yeah. So that's the belief. So to underline, okay, this belief, there is it's relevant that we can reformulate this separation of this hypothesis in a way that there are no algorithms anymore. So, of course, in computer science, people love algorithms, but maybe if you want to lower bound, maybe it's better not to have them because they are complicated, very dynamic things. So it's possible to eliminate algorithms. So let me tell you the following non-obvious fact. Yeah? Let's compare the permanent and the determinant directly. So one could come up with the following idea to say, maybe I can express, I have here the permanent of a general matrix. Maybe I can express it as a determinant of a bigger matrix. Here is m by m, here is n by n. And the entries here are just affine linear functions. Question, is it possible? Answer is yes, it is possible if n is 2 to the m. Okay. We saw the proof in the boot camp, yeah, for instance. Yeah? This is possible. Question is, can we reduce the size of this determinant substantially? Yeah? Okay. Again, there's this statement. valiant hypothesis equivalent to the statement that here the size n of the determinant has to grow faster than any polynomial in M. So you have this equivalence, and you see these statements, there are no algorithms anymore. I mean, it could be a problem in algebra. So yeah, that's the problem we would like to attack. Unfortunately, should be honest as a scientist, that's what we nowadays, what we can prove is very modest. So the best known lower bound is n greater than or equal 1/2 m squared. And this bound is 10 years old, is due to Mignon-Resser. That's all what we can prove. So that's the, okay.
It's better than we can do the circuit.
Huh?
It's better than we can do the circuit.
I know. It would be wonderful to put a logarithm here. Yeah. Insiders know. Yeah. Good. Okay, so this was the first half of my talk. I think I'm good in time. So in the second half, I'd like to explain you a little bit about the ideas that are around, how one could possibly advance this field. So orbit closure problems. What is that? So the idea is to refine this basic strategy. Remember, yeah, we want to refine the basic strategy in order to attack this algorithm-free characterization for VP different from VNP. Yeah. What was the strategy? So please recall the strategy. We had a set, an affine variety, X and R. This was the variety of the easy polynomials. That is to say, the closure of the set of easy polynomials. And the strategy is to look for a resultant. It's a non-zero polynomial function R, defined on the big space, that vanishes on the easy polynomials. Okay, that's the strategy. So, okay. So we need to have more information about these resultants. Previously, we only used their existence in certain degrees, but we need to know more. So how could it be possible? Well, the idea is we replace this X and R by something else, by another algebraic variety. So we kind of change the model of computation. And this algebraic variety should have lots of symmetries. Okay, and we want to exploit these symmetries in our search for the results. That's, I think, the basic idea. Okay, so these symmetries, yeah. Okay, these resultants will have, okay, in my title that pops up the invariants. So these resultants, we will see that we can restrict our search to resultants having certain invariant properties, in which these invariant vectors are called highest weight vectors in representation theory. So I will explain more about that. But that's the basic idea. So, okay. Let me talk a little bit about orbit of determinant. So I think we all know, well, symmetries are important. And in mathematics, symmetries are described by groups. Okay? So the determinant has a lot of symmetries, which comes from the fact that it is a group homomorphism. So determinant of A times B is determinant of A times determinant of B. So, but what is the group in this context? So first I have to tell you what is the space. So here is a symbol. I think that you should remember. Poly sub n Cn square. It's the vector space of homogeneous polynomials of degree n in n square variables. So the permanent is an element here, the determinant and the permanent are elements here. So it's a big space, yeah? And we have a group acting on this space. It's the group GLN square. This is just, so the group of invertible matrices of size n squared times n squared. And what is the action? It's just a variable substitution. Okay? We just make a linear substitution of the variables. That's the action. So now, what is the orbit of the determinant? Yeah, we take the determinant and we apply all possible group elements that we think of applying all possible linear, invertible linear transformations. So what you get if you do that, I would say, it's maybe one could call it determinant in disguise. Okay? If you would write it down in an example, you wouldn't recognize anymore that's a determinant, but it has been obtained from the determinant just by this transformation. Okay. And I think it's a very interesting fact that there is an efficient algorithm to decide whether a polynomial is a determinant in disguise. So there is an algorithm by Niraj Kayal, who is also here, to determine this. Yeah? Okay. So, but what we do now, what we have to do, we have to take the closure of this orbit. So why that? Why that? So that n, this algebraic variety, is the closure of the orbit. So we add again all these limit polynomials. And why do we do that? Well, you have to recall this algorithm-free characterization of VP versus VNP. And I have modified here a little bit. So what have I done? Okay, I have chosen another variable, z, a homogenizing variable, and then I just homogenize the relation that we had before. That's a technical point, by the way. It's not so important for the overall picture. So I can just rewrite it in a homogeneous way, and instead of the permanent, I have now multiplied with this power of the linear factor. And okay, so this becomes an element of my space, poly n Cn square. Now you see, if you have this matrix, it will not be invertible. But we know, of course, any matrix can be arbitrarily close approximated by invertible ones. And as a consequence, we see that if you have this relation here, star, then this guy is in that n. So that's a very easy observation. It's no big deal. It's no big deal. Okay. And okay, so in 2001, Ketal Mulmule and Mili Zohoni, they wrote a paper in which they proposed the geometric complexity approach to this VP versus VNP problem. And this is one of the things they proposed. They said we should attack this problem via orbit closure problem. So we should try to prove this. Yeah. Okay. Okay. That's easily said, but how can we possibly do it? Yeah. How can we possibly do it? Okay. So I should say at this point, to make clear the connection, orbit closures are studied in a field of mathematics which is called geometric invariant theory. So this is, again, is a field that mixes algebraic geometry and representation theory. Okay. Good. So now I will tell you what we have tried, the people have tried to advance with this. Yeah. What are the ideas? It's a collection of, I think, ideas that are very beautiful, but so far the success has been limited. But we're advancing. So okay, decomposition of function spaces via symmetries. So what do I mean by that? Yeah. So recall these resultants. The resultants are functions R from our space of forms, complex valued, that vanish on that n. So the collection of all these resultants is called the vanishing ideal of that n. Okay? So how can we understand this? Now, okay. Right. So another notation. It's just like that. So we're looking. Okay. We are looking of the set of those R. So these are polynomial functions on a set, on a space of polynomial functions. So it's just the space where the R's lie is a space I call poly. Yeah? It's the vector space of polynomial functions on poly n Cn square. That's how it is. Yeah? Enormous space. And what we have this group action on this space. This was the variable substitution. This immediately induces a linear action of the group on the space of functions. This is the usual thing. Okay, and it's important that because the determinant dit n, this algebraic variety, is invariant under the group action, also this vanishing ideal will be preserved under the group action. So that's an information that we want to use. Okay, so what we have here, so we have a vector space with a linear action of the group. Representation theory is the study of that. It's the study of linear actions of groups on vector spaces. It's not only important in mathematics, it's of great relevance in quantum mechanics, where you also have this setting, exactly this setting. And what do we try to do? Okay, whenever we have a representation, we try to split it into smaller parts. Yeah? we try to split it into a direct sum of irreducible subrepresentations, which corresponds to a simultaneous block decomposition. It's like if you have a matrix and you diagonalize it, then the blocks are just one by one. But here we want to, each group element gives a linear transformation, and we want to have a block decomposition that is simultaneous for all transformations. That is what's, okay. Representation theory tells us in principle how to do this. And of course, this gives a reduction of the problem size. Now, all these types, okay, I can't explain everything in this lecture, but these irreducible subrepresentations that we get, they can be classified according to isomorphy. And what is interesting, if you do that for this general linear group over the complex numbers, those are labeled by discrete quantities, namely vectors of integers. So, I mean, these types are labeled by some vectors lambda in Cn squared. I may assume that they are monotonically decreasing. So this is discrete information, which is, by the way, somehow related to atomic spectra that may be discrete. So this is all connected. Okay, I call those V lambda. Now, what do we try to do? So we have this enormous space. Now I have put this, the letter D here, meaning that now I look for resultants in degree D. And okay, I have this decomposition in the irreducible subrepresentations, and those appear with a certain multiplicity, which I have denoted plat lambda. So this is a natural number, which gives me the multiplicity with it. This appears. Okay, platism. Okay. Right. So this problem. It's a very old problem. Now, think of replacing this n squared by 2. Okay. Then what do we have? What is the poly n of n squared? These are forms of degree n in two variables, binary forms. Okay? This was a major subject of study in the 19th century in invariant theory. So important mathematicians like Cayley, Sylvester, Clebsch, Gordon, Hilbert, they worked on that, and they tried to understand the invariants, so-called covariants of binary forms. And understanding those leads to this decomposition where you put here a 2. Okay? So this is quite well understood, but if you don't have binary forms, if you have ternary forms or forms in more variables, it becomes considerably more difficult, and these platism coefficients are not too well understood, unfortunately. Okay. Okay, there is another, Kronecker coefficients, what's that? That's very important in our context. Okay, now I have to switch a little bit. I talked a lot about this determinant, very difficult problem, but most of the ideas that I was explaining work also in another setting, namely in the setting of tensors of order 3 or trilinear forms. So remember, I talked about the matrix multiplication problem. This can be reformulated as the problem of tensor rank. I don't have the time to explain all the details, but the space that we consider now is this tensor product of the 3 vector spaces, and the elements here, you can think of them as trilinear forms. Yeah? And I tried to play the same game. Yeah? The same game. And if I do that, I have to study this decomposition, again. And these are called Kronecker coefficients. So, okay, I know this cannot be understood in detail, but I hopefully you will see the great picture. So these Kronecker coefficients, they show up in the tensor rank problem, but they also show up in this resultant-based approach to VP versus VNP. They show up everywhere. So they are omnipresent. But the problem, again, is that these Kronecker coefficients, they are natural numbers, but we don't know of a combinatorial description. We would think of these count something, but it's not known. Okay, we can write them as for the specialist, it's not known whether the function is in sharp P. We know that's in gap P. It's a difference of 2 set functions, but we don't know what it counts. So that's a handicap here advancing with this. Okay, now I should. Now the good news. I mean, why I'm optimistic that one can advance along these lines? Well, this idea of resultants in the tensor setting has been successful so far. Yeah. So again, it was Strassen with the pioneering work in '83. He was the first to come up with such a resultant in the tensor setting. He came up with an invariant, a new invariant that nobody had seen before, and a resultant that vanishes on all tensors of border rank 3.5. So he had this example, and with this he proved the lower bound on border rank. And then much later, 15 years later, Markus Bläser, at that time a PhD student in Bonn, found a world record for the lower bound of for the rank of matrix multiplication, and I think very important part of his proof was this resultant by Strassen. So, and then very recently there was a result, a paper by Landsberg and Ottaviani, who finally managed to improve the lower bound by Bläser. And what did they do? What is the actually there was another paper by Landsberg which built it on that. But what was essential? Well, they found they were managed to extend this construction by Strassen. So they came up with another resultant. Okay, and they were guided by representation theory. And another result, very recent, so by Christian Ickenmeyer, John Hauenstein, Joseph Landsberg, all in this program, there was a proof, a resultant-based proof, that the border rank of 2 by 2 matrix multiplication equals 7, using a resultant, or highest vector, of degree 20. So, okay, these are small examples, it look like, but if, okay, the problem behind are quite difficult, and we have to go to families, of course. Yeah. Right, so, okay, after this intermezzo about the tensor setting and about the successes, let's go back to the determinant, the big problem. Let me tell you a little more about the ideas here, and what we know. So I have this vanishing ideal of the determinant which consists of the resultants we are looking for. This is a decomposition of the overall space with these Platt-Whitman coefficients. Now I just think of, I have this vanishing ideal in degree D. It's a subrepresentation. It must split somehow. I don't know how. But the multiplicities I call mult-det. And I would like to know these multiplicities. Why? Well, this multiplicity tells me if this is free, for instance, I know I have 3 linearly independent resultants of this certain type. Clearly, I want to know this number. Okay? Right. And here is a result that tells us about what we know about these multiplicities. So this is okay, due to Malmolay and Sohoni, and then it was refined and clarified in a joint paper with Landsberg, Manival, and Weyman. So we have these inequalities. These inequalities, of course, trivial, but this inequality is important. It says this multiplicity here is at least the Platt-Whitman coefficient minus some Kronecker coefficient. Yeah? What you would like to have, that this is big. And what is this Kronecker coefficient? If you remember, the Kronecker coefficients are functions of 3 partitions. And here, of these 3, 2 of them must be rectangular. So these are rectangular partitions. Yeah? This is the Kron lambda. Okay, and this is, gives very valuable information about these multiplicities. So I show you an example, a small example. N equals 3. So we're talking about 3 by 3 determinant. There have been extensive computer computations by Christian Ickenmeyer, who is here. Okay, so our space is the space of cubic forms in 9 variables. If you calculate it, it has dimension 165. Okay? Okay, and then Christian found that in degree 12, there are many types lambda with the property that the Kronecker coefficient is strictly smaller than the Platt-Whitman coefficients, which implies that this multiplicity of the determinant is positive. Yeah? And the one of shortest length is this guy here. It's this position. 13, 13, 2, 2, 2, 2, 2. If you add this up, you get 36. You have 7 components. And it turns out that for this lambda, the Plathysian coefficient is 1. Okay? Multiplicity 1. The Kronecker coefficient is 0. As a consequence of this theorem from before, this multiplicity is 1. So what does it mean? Okay? It means that up to scaling factor, we have a unique homogeneous polynomial R of degree 12 of this type lambda. So it's a function from here, from this space of dimension 165 to C. It has degree 12. It has this type. There's only one. Okay? And this guy R vanishes on this determinant variety. Yeah? So to give you an idea that this is a difficult problem, I mean, R is an element of this space. This is the poly-poly space. Yeah? Polynomials of degree 12 in these many variables. And if you calculate the dimension of this space, you get 1.3 times 10 to the 19. And I checked it in Wikipedia. The age of the sun in seconds is less than this number. So we found something in a space of that enormous dimension. And clearly, this can only be done when you use some tools, which are representations here. And in this case, lots of computer computations. Okay, and then that's why you see that this example is not that small and why it's difficult to go further along these lines. So, okay, last section of my talk. Yeah, occurrence obstructions. Now, this is an idea, I think an elegant idea, to go further. It's not clear that it will work, but one has to be optimistic. Okay? So the idea is due to Malmolay and Sohony, goes back to them. They said, okay, let's do the following. Forget about these individual resultants. We only want to know about the type. It's a simplification of the whole story. Only think about the type. Okay, and then let's call a candidate for occurrence obstruction. It's my naming, it's not their naming. A candidate is a type lambda such that this multiplicity, that lambda, equals the Plathysian coefficient. This means that all polynomials R of type lambda vanish on that n. All of them. Okay? Now, if you have this, when such a candidate, when do you get a real occurrence obstruction? Well, if additionally you can find one polynomial R of this type lambda which does not vanish on this padded permanent. If you have this, then you are done. Okay? So, then now we look for these candidates, just for the candidates. And by the previous theorem that I mentioned, I have the following implication. If the Kronecker coefficients here, lambda, rectangular, equals 0, then lambda is a candidate for occurrence obstructions. Okay, we have some combinatorial condition, but the converse is false. It's not an if and only if. So we give it a try. Yeah? Okay. Right. So we are looking for lambdas where this Kronecker is 0. So what is the state of the art regarding these occurrence obstructions? So, okay, to be honest, so far we don't have any examples of occurrence obstructions in this setting. Don't know. Yeah? And I mean, I think for two reasons. One reason is I think the mathematical theory is quite involved. And it's not easy. If you lack the theory, you can try experiments. But here, the dimensions are so huge that experiments are extremely hard to perform. It's different in the tensor situation where it's easier to do experiments. Here, the dimensions are enormous. The good news is that in the tensor setting, with Christian Ickemeyer, recently I found an explicit family of occurrence obstructions. So we use this to prove some modest lower bound on the border rank of the matrix multiplication tensor. So this is the first time that, this idea of occurrence obstructions was put to work, even though in a simpler setting. Okay. I'm almost done. There are some theoretical results about these occurrence obstructions. So this is the set of the bad guys. You remember the candidates are those lambda where I have an equality here. So let's define this set where this is violated, that these are the non-candidates. And they have a structure. One can prove they are a monoid. So if I have two lambdas, I can just add them, and this thing is closed under addition. So one can prove from general principles it's a finely generated monoid. Yeah? And we could try to determine it. This, yeah. And there is the idea of looking at the saturation. It's like going to a cone. So this is a bit technical. This consists of those lambda with the property that a multiple of this lambda with a k that is a natural number, positive natural number, is contained here. So this is like essentially going over to a cone. Yeah. And we'd like to understand this for finding, actually, because we want to find point outside this monoid, because these are all the bad guys. But there is a result, again, says that it's difficult. It's, actually, these are two papers, one with Matthias Christian, the other was Shravan Kumar. And this says that the saturation of this monoid contains all types of lengths less than or equal m, meaning that this is very, very big. And we have to, we should find lambdas that are not contained in that. Now you have this saturation. It's almost everything. So that's why it's very difficult to find these candidates. It's, for the expert, this means that you have to look for the holes in these monoids, and holes are very hard to analyze. Okay. So, okay, that somehow explains the difficulties here. And now this is my last transparency. Okay, to finish, I'd like to talk about something that already happened while we were here at the Simons Institute in the last 2 weeks. So on the search for these vanishing Kronecker coefficients. So in this sad paper with Christian Nickemeyer, we analyzed Kronecker coefficients, and we came up with an upper bound. So even though we don't know that this counts something, we came up with a counting function t, which is an upper bound to Kronecker coefficients. And where it is known that testing the positivity of this is NP complete. So I could explain to you, if you want, offline what this t is. It's quite nice. Yeah? So I wasn't happy with this result because I believed, because Ketan had said so, that it should be testing positivity of Kronecker coefficients should be doable in polynomial time. Now, if you look at this, it doesn't look like this were the case. So this made me maybe rather depressed. But then Ketan came and pointed out a positive consequence. He said, well, why is it good to have this? Well, whenever you have such an NP complete problem, it means there must be many lambda mu nu where this is 0. Yeah, if you have an NP complete language, it must be quite big, and the complement also must be quite big. That's general principle. So as a consequence, one can conclude there are super polynomial many triples of length at most on where the Kronecker is 0. They can even be explicitly constructed. And so this it's a success of complexity, because if you tell these people in algebraic combinatorics, they don't know how to do this. So it's quite indirect. So of course, what one tries to do now, how about, I'm interested in those guys where mu equals nu is a rectangle. So the hope was then, of course, that if we restrict this, it will still be NP complete. But unfortunately, it turns out if these are rectangles, this is always positive. So doesn't of course mean, again, Christian pointed out this very quickly. So the argument breaks down, But still, I mean, maybe one can save the argument by replacing this t by some function which is more complicated, something in between. Should be more complicated than t, but maybe not as complicated as this. Maybe it can be saved, the argument. But this is unclear. So that's all I wanted to say. I hope I wasn't too technical and was able to give you some Okay, some overview and also show you some of the excitement that we have here in doing this kind of research. Thank you. I didn't say, this is was the transparency with the small example.
Yeah.
Well,
Right at the end of part 2 of your talk.
You know, I didn't talk about the permanent determinant problem. Maybe I. Okay, let me go back. This, okay. Well, you don't, from this you don't get any conclusion about permanent versus determinant. The problem is just too small. Yeah, but what I found a function, I found a resultant that vanishes on debt-free. Okay. So I mean, what you can use it if you want to prove that a certain polynomial is not contained here. Yeah, then you can use these functions. For instance, if you have a form that depends, okay, yeah, which has at most 7 variables, a generic one, then you prove the determinant complexity of that is at least so, yep. Okay, did I?
So in first part of the lecture, we have explicit polynomial, which you showed that it requires exponential time to compute. Why doesn't this imply that VP is non-equal to VNP?
Well, the explicit polynomial had these square roots. Okay, so this doesn't fit this model.
Cannot you prove some kind of generic argument that if you have some explicit polynomial over C, then it must be some situation over some prime number where it also requires exponential? No.
I don't think that one can have these ideas. One could also have the idea if you have these square roots, then you just approximate it up to a certain number of digits. Then this would be explicit. Okay, this is an idea. One can try all these things, but as I said, okay, if you manage to do it for a p-definable family, then you have proved variance conjecture. And I don't think that this can work along these lines.
Okay, so well, maybe the last one back there.
Are there natural proof like variance for variance conjecture?
Sorry, I did not understand.
Are there barriers such as the natural proof barrier for variance conjecture?
Okay, I can try to read whether there is a natural proof barrier for variance conjecture. Not that I know of. No, not that I know of.
Does the notion even exist?
I don't think that it is clear what it would mean exactly. So that yeah. The notion of a natural proof in the algebraic complexity setting.
But it must exist. Since there is an implication that this implies that P is not equal to P.
No, it follows.
Oh, it follows, right? Okay.
Yeah.
So, right, okay.
That's a question that is asked quite often.
Exactly.
It's a question.
Follows.
You should start by defining pseudo-random generators and algebraic.
Yeah. All these things are, yeah. It has not been developed in detail, no. Yeah.
Okay, maybe we'll take the chance to thank Peter again. So Peter and many of the people mentioned in the talk will be here for the whole semester. So please come over to the Science Institute, the Round Building, Calvin Hall. Next week, there's a workshop on geometry.